In this last lesson, we're going to talk about quadratic equations with complex solutions. So we want to remember that the roots or zeros or x-intercepts of any quadratic equation can be found with the quadratic formula. Since this formula contains a square root, right here, it is fair to investigate solutions to quadratic equations now when the quantity b squared minus 4ac, so that's this expression under the radical, known as the discriminant, is negative. So we call that b squared minus 4ac the discriminant. We have a vocabulary word for it now. So looking at the first one, we have a quadratic x squared minus 4x plus 29, and we're going to find the solutions to the equation. Whenever I see directions like this, they can be confusing because right now nothing about this problem has to do with complex numbers, but that tells me that if I solve this equation with the quadratic formula, I should expect to have complex answers. So we're going to plug those numbers into the quadratic formula. We have negative 4, because our b value is negative 4. Just label these. Plus or minus the square root of negative 4 squared minus 4 times 1 times 29. That's going to be all over 2 times 1. So that's going to simplify to 4 plus or minus, if I type the discriminant, which we can now call this the discriminant, in my calculator, I get negative 100. But we're going to slow down for a second, and when I look at this, I could tell this was going to be negative before I typed it in my calculator, because when I look at the b squared, right, that's going to be 16, and even though maybe I don't know this part in my head, I can tell that that's going to be bigger. So I'm doing 16 minus something bigger than 16, right? So I know I'm going to get a negative number. And that negative number, the value we get for the discriminant, is negative 100 over 2. So we can keep going now. Before we would have said that this doesn't have any real solutions, which is still true, but it does have complex ones. So I have 4 plus or minus the square root of negative 100 is 10i over 2. And then we can simplify it. And we get 2 plus or minus 5i. So this is going to be 2 minus 5i and 2 plus 5i. And there, as promised, are our answers in simplest a plus bi form. Now, we have been going back to those graphs and how would this look graphically? So what does it mean, and we did kind of look at this 2 lessons ago, what does it mean for a graph to have complex solutions? How is that going to impact how the graph looks? So if I graph this on my calculator, I actually wouldn't see anything with a 10 by 10 window. But if I moved my y values up all the way to 50, let's say, we would see that the quadratic is somewhere in here, and that minimum value is above 20. Okay, so you just have to change your window, it is there. So we can see it doesn't have to be that high, but basically we see that when we have these complex solutions, if we graph this quadratic, right, we just graphed this, that it's not going to cross the x-axis. So if the solutions are complex, the graph does not cross the x-axis. Okay? Now, before we solve more of these equations, we're going to talk more about predicting things from original equations. So this says there's a battle going on between b squared and 4ac. And I already alluded to that when we looked at this. Remember how we said which one's going to be bigger, the b squared or the 4ac? So in every quadratic equation, there is a battle going on between b squared and 4ac. If b squared is larger than 4ac, b squared minus 4ac will be positive. The graph will have 2 real roots and cross the x-axis twice, like all good quadratics, the ones you learned about in Algebra 1. anchored in place, roots that enter the ground, just like in real life. So we call those spots that it crosses roots because it's almost like you have a plant here and it's rooted or anchored to the ground at the x-intercepts. Now most of the quadratics, unless your teacher showed you a counterexample in Algebra 1, always cross twice. So that would have been back on my equation if this number had been bigger, like maybe I had 12 squared, right? 12 squared would be bigger than 4 times 1 times 29, and then this would have been positive, right? That discriminant would be positive, and I would have had those two real roots. Now in our problem, if 4ac is larger than b squared, so that 4 times 1 times 29 was bigger than negative 4 squared, right? Or 4 squared would be fine too, right? 16 compared to what that second part is, which is 116. B squared minus 4ac will be negative. The graph will have imaginary or complex roots. The graph will be located completely above, so that's what we saw here. Or it could also be completely below. So if you had a negative x squared graph, that could be completely below the x-axis, anchored nowhere, floating in space. Now, you can go through and every single time do the quadratic formula, or if you have a graphing calculator on hand like we do in the 21st century, you can always just look at the graph and see what it looks like. But imagine you don't have a graphing calculator with you, you live, in the past when they didn't have graphing calculators, you can quickly look at quadratic equations to know whether or not they're going to cross the x-axis. So here's a couple of hints. If either A or C, sorry, I'm going to move this up, is negative, just one of them, the roots are real because 4ac decided to work with instead of against b squared. So if I have a quadratic like this, let's say x squared plus 5x minus 7 equals 0. So if I thought about the discriminant, just that piece that goes in the square root, that would be b squared minus 4ac. So 5 squared minus 4 times 1 times negative 7. So as soon as I have that one negative sign, that's going to cancel with this negative sign, and it has to be positive, right? Because we're going to get 25 plus 28 in this case. There's no way that they're even working against each other. They're working together. It says sometimes b is so large in comparison with ac that you can tell the roots will be real. So let's say I had x squared plus 10x plus 2. I can tell because this value of b is so large, and even negative 10 would work, right? Because we're just squaring that, it's b squared, so I want to point out positive or negative doesn't matter in terms of the b, it's the absolute value of that number. So if it has a large absolute value, the b is going to win out. Sometimes a and c are so large in the same sign, you can tell that the roots will be imaginary. So if I have x squared, maybe 3x squared plus 2x plus 8 equals 0, this is b squared is only going to give me 2 squared. And this is 4 times 3 times 8. I don't even have to write that down. I can tell that that discriminant is going to be negative and will have imaginary roots. Now there is one other special case, and I'm going to erase this, that we didn't talk about, and we haven't really looked at a graph like this unit. It says when b squared equals 4ac, the graph is literally hanging onto the x-axis by a thread, also known as tangent to the x-axis or a double root. Real equal roots at the same location. Look at an example of that. So if I have x squared plus 6x plus 9 for my quadratic, if I did the discriminant, that would be 6 squared minus 4 times 1 times 9. So that gives me 0. So if I think about my quadratic formula, and even though we didn't talk too much about the graphs, we did have one where the discriminant was 0 in the quadratic formula lesson. Basically, that graph, the plus or minus 0 is going to give me the same answer. And if I graphed that quadratic, it would look like this. Basically just touching here and it has it looks like one root, but we call it a double root. It basically has two equal roots, and if you remember from circles in geometry, when something's tangent, it just touches at one spot. So if we just move this quadratic down just a little bit, we'd get two roots. If we moved it up just a little bit, we'd have imaginary roots. So this is kind of that middle case where the b squared and the 4ac are equal, so we end up with a discriminant of 0.